Pop quiz. If a sealed balloon's volume is cut to 1/2 at constant temperature and number of particles, what happens to the pressure? Does it double, halve, or stay the same? 5 seconds. Go. The answer is it doubles. Because pressure and volume are inversely related when other factors stay constant. In this video, you'll learn how pressure, P, volume, V, temperature, T, and amount of gas, N, connect. How Boyle's, Charles's, and Gay-Lussac's laws fit together, how to use the ideal gas formula, and how to avoid common mistakes. Let's start. Picture a gas as countless tiny particles flying in random directions. When they hit the container walls, they exert force and spread over an area. That's what we call pressure. Next, imagine what happens as the temperature changes. Hotter gas means faster particles, and faster particles make stronger impacts. Now, to study gases, scientists often use an idealized model. The ideal gas assumes point-sized particles, no attractions or repulsions, and perfectly elastic collisions. It's not reality, but it provides a powerful first approximation. From this model, we can identify some key gas laws. First, Boyle's law. At constant temperature and amount of gas, pressure is inversely proportional to volume. In other words, squeeze the volume, and the pressure rises. Meanwhile, let the volume expand and the pressure drops. Second, Charles's law. At constant pressure and amount, volume is directly proportional to temperature in Kelvin. Warm a gas and it expands. Cool it and it contracts. Third, Gay-Lussac's law. At constant volume and amount, pressure is directly proportional to temperature in Kelvin. Heat raises particle speed. Faster impacts mean higher pressure. Taken together, these three simple relationships combine into the ideal gas law. P times V equals N times R times T. Here, P is pressure, V is volume, N is the number of moles of gas, R is the gas constant, and T is temperature in Kelvin. Alternatively, on the molecular scale, P times V equals N times K sub B times T. In this form, N is the number of molecules, and K sub B is Boltzmann's constant, about 1.38 times 10 to the minus 23 joules per Kelvin. Be careful, temperatures must always be in Kelvin, and volume should be in cubic meters or liters, matched consistently to the units of R or K sub B. So far, we've seen how these three simple relationships knit together into the ideal gas law. P times V equals N times R times T, our go-to model for gases. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Now, let's apply the law. Imagine the same canister of gas at the same volume. If the temperature rises from 300 Kelvin to 450 Kelvin, pressure scales directly with temperature. The formula reads P2 equals P1 times T2 over T1. Substituting the numbers, 1.00 atmospheres times 450 over 300 gives 1.50 atmospheres. Same volume, more thermal energy. So the pressure increases. Next, let's do a full calculation. Suppose we have 0.50 moles of gas at a temperature of 300 Kelvin in a volume of 10.0 liters. We want to find the pressure, using R, the gas constant, as 0.082057 liter atmosphere per mole. Kelvin, the equation becomes P equals N times R times T divided by V. That is 0.50 times 0.082057 times 300 divided by 10.0. The result is about 1.23 atmospheres. Notice how keeping units consistent makes the calculation straightforward. We chose the liter atmosphere version of R to match our setup. Before we wrap up, here are common mistakes to avoid. 1. Using degrees Celsius instead of Kelvin, always add 273.15. 2. Mixing units, like milliliters versus liters, or pascals versus atmospheres. 3. Grabbing the wrong R value. Make sure R matches the pressure volume units you're working with. Once the units line up, the math usually becomes a single clean step. Of course, real gases aren't perfect at high pressures or low temperatures. Molecules take up space and attract each other, so behavior deviates from the ideal gas law. On the other hand, at modest pressures and warm temperatures, the ideal model works surprisingly well. And you can see these principles in action all around you. Pressure cookers raise the pressure by heating food at nearly a fixed volume. Aerosol cans warn you not to overheat because pressure climbs with temperature, and hot air balloons rise because hotter air expands and lowers density. Same principles, different contexts. To recap, the ideal gas law states that P times V equals N times R times T. This ties pressure, volume, temperature, and amount of gas. Always make sure to match your units and convert temperatures to Kelvin. Then, apply the special cases, Boyle's law, Charles's law, and Gay-Lussac's law, and you'll be set for most gas problems. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.